So far, you've been taught that nucleophiles are electron-rich species, electrophiles are electron-poor species, and chemical reactions happen when electrons flow from nucleophiles to electrophiles. Like water moving over a waterfall, electrons want to move from regions of high energy to regions of low energy, and the way this happens is through linear electron flow from the nucleophile to electrophile. If you take a look at the examples here, you can see that in this lesson and in the upcoming lessons, we're going to poke some holes into this idea of linear electron flow. In particular, if you look at all three of these reactions, what you should notice is that all three involve the cyclic movement of electrons between conjugated pi systems. These three classes of reactions will be covered in the upcoming webcasts, but the one we're going to focus on for this lesson is the cycloaddition reaction, in which two separate pi systems combine to form a ring structure. It's worth thinking about before we continue what the driving force might be for each of these reactions. Even though there's no clear nucleophile or electrophile, there are definite potential driving forces for these reactions, and the driving forces have to do with the fact that sigma bonds are exchanged for pi bonds, and there's a definite difference in energy between pi bonds and sigma bonds. So as you've learned before, sigma bonds are lower in energy than pi bonds. And as you might imagine, because we exchange two pi bonds for two sigma bonds in the cycloaddition reaction, the formation of a cyclic product through a cycloaddition reaction is often highly favored. You should notice that in the product we have two new sigma bonds at the expense of two pi bonds in the starting materials, with the third pi bond migrating over to this new position. So there are driving forces for these paracyclic reactions, but I would invite you to pause the video now and take a short look at the sigmatropic rearrangement and electrocyclic rearrangements and see if you can identify driving forces, or if there are driving forces at all for either of the reactions shown here. The Diels-Alder reaction is without a doubt the most famous and beloved example of cycloaddition. In this reaction, a 4-electron pi system, or diene, combines with a 2-electron pi system, called the dienophile, in order to form a 6-membered cyclohexene ring. The reaction forms two new sigma bonds between the ends of the diene and dienophile at the expense of two pi bonds in the starting materials. Although it isn't strictly required, we often polarize one or both of the substrates in order to encourage the reaction to proceed, making one substrate more electrophile-like and one more nucleophile-like. In the example here, you can see we've added an acetyl group to the dienophile in order to make it more electron-poor and more electrophile-like. Diels-Alder reactions work best with electron-poor dienophiles, and electron-poor dienophiles are often easily accessible, widely available substrates like alpha-beta unsaturated ketones. Anytime you see a cyclohexene ring as a product, you should think about making it through the Diels-Alder reaction. An advantage of pericyclic reactions is that you can easily run the curved arrows in reverse to get from the product back to the likely reactants. Analyzing this product, for instance, we can see that the double bond in the product connects the two inner carbons of the original diene. The electron withdrawing acetyl group was likely part of the original starting dienophile, and running the electron flow arrows in reverse confirms this. So if we run these electron flow arrows in reverse to generate the starting materials, what we can see is that indeed the dienophile is methyl vinyl ketone and the diene is simply butadiene, and combining these two substrates and running the electron flow arrows in the forward direction gets us from the starting materials to the product. I invite you to pause the video now and see if you can identify the portion of this molecule that was formed using the Diels-Alder reaction. In the next webcast, we'll take a look at some interesting observations about the Regio Selectivity of the Diels-Alder cycloaddition. As you might imagine, adding substituents to the diene and dienophile has the potential to substantially complicate the reaction. Lucky for us, there are several simple rules backed by orbital considerations and resonance considerations that allow one to easily predict the regioselectivity of the Diels-Alder reaction.